Good morning, good afternoon, and welcome to this ISE HESI joint webinar. My name is Sandrine Degla, and I'm a senior advisor for the Center for Environmental and Ecological Health here at HESI, and I also manage HESI's Environmental Epidemiology Committee. So before we start with our webinar, I wanted to briefly introduce HESI for those of you who do not know the organization. So I've just one slide, and I'm not going to spend too much time on this, but HESI stands for Health and Environmental Sciences Institute, and we are a nonprofit organization located in Washington, D.C. So we have a small office in Washington, D.C., but we do work internationally with thousands of scientists. And the mission of HESI is to create a collaborative environment in which we bring scientists from government, academia, industry, NGOs, and other partners to solve problems that pertain to ecological and human health. So here you have a list of our committees, and we have a couple of new programs right now. And so I would encourage you to look at our website if you want to learn more about HESI. You can also contact me. You're going to have my contact information a little later in the webinar here. So because I don't want to steal too much time away from our speaker, that's all I'm going to say about the organization. But to learn more about us, again, feel free to get in touch. And with that, I'm just going to give the floor to David Miller, who is the co-chair of the Environmental Epidemiology Committee, and who is going to introduce our webinar and our speaker. So,
Great. Thank
David.
you. Thank you, Sandrine. Okay. Today's presentation will be by Dr. Igor Borsten from Drexel University. On that, the title is Recall Bias in Population-Based Case Control Studies of Ovarian Cancer and Genital Talc Powder Use. I'll mention there's a preprint available. So if folks are interested, we'll make the slides available afterwards, but they can either photograph the QR code or wait for the slides and do the click. That's where the preprint from October of last year is available if folks are interested. Next slide, please, Sandra. Yeah, and I just kind of remind folks about kind of where we've come from. We had a presentation by Dr. Timothy Lash in fall of 2025, quantitative bias analysis, the good, the bad, and the ugly. That is available on the websites that I'll refer to later. It's recorded if folks are interested in viewing that for the first time or reviewing it on that. And then the next scheduled presentation, I'll just note, is scheduled for April 16 at 11 a.m. It will be by Dr. Rachel Hughes from Bristol University in the UK, and the title will be Flexible Monte Carlo Quantitative Bias Analysis for Unmeasured Confounding. I'll mention, too, that more sessions are being planned for 2026. We'll have one prior to the ISE annual meeting in Munich in summer 2026 on that. I will say also that registration just opened for that just the last couple of days if folks are interested. And then we're also planning one for fall 2026. What we're thinking about is having a more interactive one, basically, where if folks want to have their own data or want us to work through the data, for example, with them. Igor has volunteered in fall 2026 to kind of maybe make that as a presentation, kind of a one where basically is using your data to kind of run through some of the material. So think about that if you have interest in this and interested in having it, walking through it basically as one of these presentations on that. Next slide, Sandrine. Sandrine, I've also mentioned that I am the chair of the ISEE Special Interest Group on Quantitative Bias Analysis. The goal of that is to promote awareness and uptake of QBA methods in environmental epi by fostering ongoing dialogue, education, shared resources, and community building. There are a couple things I'll just note about that. Again, the QR code and the web link are shown here. A couple of websites. The overall SIG Special Interest Group website is available there. And within that, there's a special QBA SIG website, which contains a lot additional information, references, and that's where you can also go to look at the replays, the slides, for example, on that. And then I'll also mention we have ISE annual meetings. The last one was in Atlanta last year. We did an introductory QBA SIG meeting. I anticipate we'll probably also have that same thing in Munich in 2026 this year. And I'll also note that we've submitted a proposal. We don't know whether it'll be accepted or not on QBA and sensitivity analysis. The proposal is entitled, the symposium would be entitled Making Uncertainty Count, Quantitative Strategies for Addressing Bias in Environmental Epidemiology. And the other thing we're doing is, as you know, obviously it would be the quarterly webinars that we're aiming. This is being done jointly with the Health and Environmental Science Institute on that. Next slide, Sandrine. And then also just the HESI's, as Sandrine had mentioned, Environmental Epidemiology Committee. The mission is to take action to help realize the full potential of epi data in risk assessment and regulatory decision making. The committee was launched in 2017. Academia, government, and industry are all represented on the committee, and it emerged from the belief back in 2017 that epi evidence can play a greater role in human health risk assessment. A number of things have been organized by the HESI group. Environmental Epi group. There's a webinar series which highlights the critical role that Epi can play in QBA and showcases some of the ongoing efforts in this. Various articles have been published, and one activity of this overall environmental epi committee is the variety of QBA activities. The goal of them is to increase the understanding of QBA and make it accessible to users lacking the necessary coding and statistical skills on that. Next slide, please. Yeah, the other thing I'll mention is encourage folks. You'll see this link on the next slide when I introduce Dr. Burston. But we'd be very interested. It's a short survey. If you have thoughts about it, additional ideas, for example, we'd encourage you to look at basically and fill in the audience survey. The link is here, but it's also on the next slide that you can take a photo of when I'm introducing Dr. Burston. Having that. Next slide, Sandrine. Okay, so here's just without further ado, I'll just introduce Dr. Burston on that. Here's a bit of speaker bio on that before he begins. Dr. Burston is an educator and researcher in the field of environmental and occupational health with training in both epidemiology and occupational hygiene. He has both a BSc in microbiology and an MSc in occupational hygiene from the University of British Columbia, as well as a PhD in environmental and occupational health from Utrecht University. He's a tenured faculty member at Drexel University in Pennsylvania. His methodological expertise lies in the area of measurement error, misclassification, and confounding as they apply to observational data in epidemiology. His achievements have been recognized by the Canadian Journal of Statistics Award in 2022 for contributions to a paper on dose response modeling and outstanding contribution to epidemiology award in 2019 from the American College of Epidemiology. He's a founding member of the Global Epidemiology Institute and editor-in-chief of the journal Global Epidemiology. So with that, I will introduce Dr. Burston, and the floor is yours.
Thank you very much, David. I appreciate the introduction and the opportunity to share some of my work with you. I know I bullied my way into presenting today because I'm involved in organizing all these activities, but I really appreciate everybody who showed up here to listen to this talk that is near and dear to our hearts. So the subject of today's presentation is really dealing, the overall umbrella question is how we tackle recall bias in population-based case control studies. It is motivated by the question of surrounding ovarian cancer risk due to genital talcum powder use. And as David mentioned, if you're interested in details of this work, all of it, all the mathematical details, all the code is in a preprint. The paper is undergoing review now. We revised it, including the title, to make it more accurate. And there's basically, we expect to be published soon. So, but you will have access to all the results I present to you today if you look at the preprint, except for some additional sensitivity analysis, interval sensitivity analysis that I will share with you for the first time. So I would like to give credits to my co-authors, JD, Bill Thompson, Jin Kwan, and Ken Munt. They're based at UMass Amherst as well, and Bill is an independent contractor. I mean, was a fantastic team. They had some questions about methodologies that I had some expertise in. We had a conversation and then ended up doing a project together. This is, in my experience, how some of the studies that I find most gratifying come together. It's important to disclose conflicts of interest at the start of my talk. Um, Both Bill and Ken served as expert witnesses for the defense in litigation that involves talc, and they're involved in consulting work to sponsors of the study, which is Eurotalc, a trade association that producers who are, of course, very much interested in the fate of their product and are supporting this work. Uh, the rest of us don't have any apparent conflicts of interest, except that perhaps we want to continue doing this work, perhaps with support of the same sponsor, and we have some applications pending for that. And I personally have advocated for use of quantitative bias analysis for more than 20 years. And so my perspective is clearly tinted in favor of these analyses being useful. And in fact, my award for American College of Epidemiology is explicitly for promoting Bayesian approaches to epidemiology. And of course, as I mentioned already, Eurotalc provided financial support for this work. They had no role in any of the calculations. I haven't seen the paper before it was submitted, but they did provide financial support. This is a slide on talcum powder. This is the extent of my understanding of the product, so I apologize for those who are deep experts in the subject matter. It is a mineral and involves magnesium, silica, and oxygen, as well as hydroxy groups. It comes from Earth, so it just lies there as mined and refined for our use. So it may contain other fibers and minerals, including asbestos. Talcum powder is useful because it absorbs moisture and prevents friction, and that is its use in personal care product and industrial applications. Prevents rashes, dry skin in people. So it is a cosmetic product, but it also has some commercial uses. Talc is a very interesting story because I used it in my classroom once upon a time as a case of chemical exposure that was evaluated with a rather ambiguous outcome by IARC. Since then, IARC upgraded their hazard assessment of talc to declare it to be probably carcinogenic to humans, so group 2A, if you're familiar with this classification. And it was based on the basis of limited evidence of cancer in humans. This 2004 publication is available for everybody's review. And it was also this updated evaluation of talc is the first time that quantitative bias analysis played a prominent role in IARC's decision. So this makes it a very interesting case study for us to consider. So this is my high-level summary of epidemiology of talcum powder and ovarian cancer. The first positive result was published in 1982 as a result of comparing exposed cases of ovarian cancer to community controls who were recruited at random among source population for cases, and controls were free of any disease, that definitely free of ovarian cancer or any other cancer as far as we know. There were 92 exposed cases, and the resulting odds ratio was around 2, with confidence intervals that suggest that if only random error was present, there is some evidence of excess risk. Elevated odds ratios tend to be reported in case control studies in ovarian cancer and talc literature, but not cohorts, with the exception of the latest report from sister study in US. And this 2004-24 publication is in fact quantitative bias analysis. So in order to really understand why one cohort seems to be giving different results than other cohorts, you really need to understand the guts and nitty-gritties of quantitative bias analysis. I will not go into that in detail today about this contents of the sister study, but we perhaps can leave it for another day if folk are interested. If we look at meta-analyses of ovarian cancer in talc literature, population-based case control studies tend to support the association, cohorts do not, and hospital-based case control studies appear to be very similar to the cohorts. The reason why I think it's important to draw a distinction between hospital-based case control study and population-based case control studies here is that in hospital-based case control studies, as we may recall, controls or reference tend to be in poor health. So that in sort of in stats 101 type rules of thumb, we suspect that in hospital-based studies, because both cases and controls are in poor health, they will make similar effort in recalling various exposures that they may have occurred to them. Whereas in a population-based case control study, there is a clear possibility of people who are in poor health, our cases, reporting exposures with different fidelity than people who are not really particularly motivated to recall what may have affected their health. So this is a classical situation where recall bias can be suspected in producing this heterogeneity of evidence, because among the three types of studies being compared here, population-based case control studies are the most likely to be susceptible to recall bias, where information on quality of exposure estimates for cases is materially different than the one for controls. Now, a little more on recall bias here. As a person who was trained in measuring exposures once upon a time, I was very disappointed when, as a doctoral student, I was told that much of the data in epidemiology is collected by questionnaires. That was completely unfamiliar territory for me in those days. I've made peace with this fact. But it is important to remember that in many practical situations, we are not able to measure what we want to study in epidemiological studies, especially observational studies and retrospective studies in particular. Again, as textbooks in epidemiology rightfully remind us, person's health can affect both accuracy of reporting and memory of past experiences, especially if there is suspicion that those experiences can be related to poor health. And this is exactly what we can credibly discuss in the context of Kramer's first positive result, where sick cases were compared to healthy controls. In technical terms, this is seen as differential exposure misclassification case, the really horrible bugbear of introductory epi classes, where your professor usually says, and we cannot do much about it because we have no idea what the impact will be. We can do something about it, but it's a much harder case for which bias can be anticipated, basically cannot be. There are some very prominent examples in recent years where recall bias and differential exposure misclassification was found to be important to interpretation of findings. I'm sure there's tons of examples going back in history, but this particular one sticks in my mind because it was an example of breast cancer and exposure to shift work, where there was very good validation data available, which showed that sensitivity and specificity were different for cases and controls. So cases were much more likely to report exposure if it happened, so they had better sensitivity, roughly speaking. Well, specificity was similar for cases and controls, even though controls were somewhat more likely to be accurate in reporting absence of shift work when that was in fact true. So this ties in with how we think recall bias operates. You will observe that these differences in sensitivity and specificity are pretty small. On the face of it, 80% in sensitivity and specificity sounds pretty good. And the differences are definitely less than 10%, a couple of percentage points, 5% points on average at most. And yet, if you do appropriate adjustment for differential misclassification here, you do get results that make essentially a positive association go away. And there's some subtleties in how to do it right, but this is an example where interpretation of a study changes, even though we can be quite certain that exposure assessment through recall and interview of patients here was pretty good. So quantitative bias analysis can help bring order to some of these considerations of quality of data that we have. And talking about history of quantitative bias analysis allows me to bring up one of my favorite stories by Alexandre Dumas, where some of these really exciting, really accomplished individuals get together 20 years later in order to reflect on their past glories and perhaps do something exciting yet again. The reason why I think it's pertinent is that a lot of the groundbreaking work on quantitative bias analysis in epidemiology is 20 years old or more. Like 20 years ago, people were already writing pretty comprehensive textbooks on the issue, which means that foundational work predates that. So this is not new. So methods to calculate how effect estimates would be different if there is no systematic errors is described in Tim Lash's book, the person who launched this seminar series before me in the fall of this year. It's a fantastic book that's survived many editions, and it's a very accessible, user-friendly text to anybody who wants to start the journey in this direction. The matter of removing bias due to misclassification of exposure is a mature area in statistics, and Paul Gustafson, for example, published a book on this in 2004. For statisticians, that means there's not much work to be done. They move on to something else. This is a problem that's been largely solved. There's not many contributions that can be made unless challenged by nuances and realities of epidemiologists. But for archetypal cases, they worked out how to deal with differential exposure classification, which is essentially recall bias. Even IRAC 20 years later thinks it's a good way to address systematic errors. There's a free book that they published in 2004. We were all very excited about this, that summarizes about a lot of that lore going back 20 years. And it is clear that epi theory practice lags behind theory, and it's natural, but there are opportunities to collaborate here with people outside of some epi silos that are established out there. And a lot of us who have been working on these quantitative bias analysis methods are quite keen to take our advocacy into other research questions and other research groups. We have this SIG, and we are all the people that I know in this field are very open to collaboration. So this is a bit of self-promotion for you yet again. I apologize for this messy algebra on this slide. The only point here is that we can go from observed to true contingency tables if we know something about sensitivity and specificity of exposure classification. Again, these equations look ugly, but it's pretty trivial to program them into Excel or however you want to do it, and go from this 2x2 table on your left, which gives you observed counts of cases and controls by exposure status, to the true counts of cases and controls on the right-hand side of this table. It is closed form algebraic solutions. If you really know what sensitivity and specificity are, you can receive a massive dividend here by not having to discuss measurement error, recall bias, and all those nuisances. You can actually know how they affected your results and report an estimate that has taken care of all that. Shorter discussion, simpler presentation of results, right? So in practice, of course, some of this gets a little messier because we almost never know what sensitivity and specificity are. We need to either estimate them from validation studies or obtain them from opinions of experts if you're a believer in Bayesian approach to these to these calculations, which I can freely admit. I've made peace with Bayesian statistics. It took a while, so if folks are unsure about it, I encourage you investing time into understanding what these methods entail. And 10, 15 years down the line, you may find yourself converted or completely opposed to them, whichever way you fall. But they cannot be easily dismissed as irrelevant anymore. So going back to the reality of the problem we're trying to face, what we're interested here is looking at case control studies of genital talc use, which were conducted in community settings. So we had cases from were ill with ovarian cancer, and we had population-based reference that were selected to match them. I will not go through individual results, but they're basically pulled out from published literature. If we are okay with pooling data across these case control studies, some of them from these reports, we end up with more than 2,000 cases who are classified as exposed. So we're definitely looking at substantial increase in knowledge on this topic compared to Kramer's work from 1982, which had only 215 matched case control pairs. Now, pooled analysis of case control studies does show suggested elevated risk of ovarian cancer, so elevated odds of ovarian cancer due to genital talc use. So this is the result that I already shared with you. There's a moderate heterogeneity in these case control studies here, which allowed people in the past to pool them, and we did not challenge that decision. We also said, okay, let's treat these case control studies as if they can all be combined together. And the data in this case is summarized by the bottom row of the table, where the 4 counts are pooled totals across individual case control studies. So this is the data set we're working with. Now, in order to proceed with adjustment for differential exposure misclassification or recall bias, we need some information on sensitivity and specificity. And here, work of IARC was indispensable in allowing us to proceed rather rapidly, because during IARC monograph meeting on talc, they conducted prior elicitation exercise as the technical jargon goes. They asked experts what they thought about sensitivity and specificity, and they reported that in the appendix to their monograph. So this is in principle not a bad start. They asked experts to provide best guesses of sensitivity and specificity separately for cohort studies and case control studies. Here we're only focusing on case control studies, which is a right-hand side of the table in front of you. Experts were asked their views on sensitivity and specificity separately for cases and controls. This, to me, acknowledges that IARC agrees that, or experts retained by IARC, IARC is not an entity, it's just an organization. People who came to the monograph meeting agreed that there was a possibility that exposure misclassification could have been differential in case control studies, at least, for whatever reason. And they had 3 people who were brave enough to share their views on both best value of misclassification parameters as well as 95% range. We don't have any details about what questions were specifically asked, what materials were provided to the experts, even though we suspect that it's the same materials that were shared at the monograph meeting. But this is a start, and you can just take the best guesses, for example, plug them into those equations from a couple of slides back, and have adjusted odds ratios here for your case control studies. It's as simple as that. It's not quite so simple because you do have ranges and you need to deal with that somehow. But this is definitely a very good beginning. And this step of eliciting priors from experts is absolutely essential to bias analysis. It would be lovely if this came from validation studies, as in the case of that breast cancer case control study and shift work. But absence that, there is enough collective wisdom in the field, I believe, to allow us to have informed opinions on misclassification parameters. We've been doing this work long enough to have some clues as to whether our exposure variables are fantastic or terrible. So if we proceed with what we call simple quantitative bias analysis, and this is where you would take just one value of sensitivity or specificity for cases and non-cases, and perform adjustment using that equation I showed you a little while ago, where you get adjusted counts, and those are presumed to be true counts, and you can use them to calculate odds ratios, right? And then you get this picture, which shows whether adjusted odds ratio became greater than observed. So if you have warm colors, it means that adjusted odds ratio got hotter. It moved away from the observed, so got larger, away from 1.3 to something that is more hazardous. Or it became colder. It went down from 1.3 to something that suggests weaker effect. This chart is busy. Some people love them, some people struggle with them, so I'll do my best to walk you through them. So across horizontal axis, we are given different control sensitivities. So we have sensitivity of exposure assessment increasing within each box. And across vertical axis, we have in each box case sensitivity that increases from 0.6 to 1. And each column represents different specificity among cases. And each row represents a different specificity among reference. The important bit takeaway for me here is that each panel here has different shading. The ones on the upper right-hand corner appear to be redder or warmer hues. That would indicate that if those constellation of parameters were true, our observed odds ratio would be too small and it would have to be adjusted up to get closer to the truth. Or some of these panels are almost universally bluish and cold colors, the color of the winter outside us right now. And that means that if those parameters are correct, then observed odds ratio of 1.3 should be pulled down to smaller values in order to arrive at a truer estimate of risk. And there is no rigorous way to decide which panel you should be focusing on. And that is not good, because we want some rules that will help us decide which of these guesses are good and which ones are lousy. It shows us a range of possibilities, but it doesn't help us so much to get at the answer we desire, because we don't know which of these settings for sensitivity analysis are correct. The other challenge in this particular example is that if you believe that one of these experts was more accurate than the other, in the case of IARC, you would get different degree of adjustment. So these different rectangles here represent different experts, a range of their individual guesses of sensitivities and specificities. And they're situated on the panels, indicating that, some expert one, would, if we use their views, they would definitely pull results towards smaller values. If we believe that expert 2 was the most accurate of them all, then some of their guesses would pull results towards smaller values, but some would lead to suggest that the estimates were higher. And that's for the left-hand panel that is most consistent with what experts of IARC told us, because that in that case, we are fixing specificity at 0.85. If we thought the specificity was a tad better than that at 0.9, which is within range of guesses that were provided, then the picture becomes even more confused, with each expert either pulling odds ratio in one direction or the other. So choice of expert here matters, and the question becomes, well, how do we account for it? Because we want to have a defensible methodology that tells a coherent story. This simple analysis with just plugging in single values, which is what IARC essentially did in their monograph, doesn't get us there. My proposal is to proceed with Bayesian adjustment. And I know I'm running the risk of losing half of my audience here because I'm going to show uglier equations, and I apologize for that. But please bear with me. This is my understanding of how Bayesian calculations proceed. We're interested in calculating probability distribution of true values given our data, which is proportional to probability of data arising given some presumed truth, some model, as well as our belief of where true parameters lie. And the parameters here include, truth here includes both magnitude of association between exposure and outcome, as well as sensitivities and specificities. So in statistical parlance, you have a posterior distribution here that is proportional to likelihood, which is what we always work in Stats 101, and priors. And the real trick here is we want to weight likelihood by priors, which is, which will give you the same answer as the usual statistical analysis, unless priors that we put here are completely uninformative. So if we say, we don't really know anything, to have any prior information to bring to the table, then these Bayesian calculations will give you exactly the same result as a numerical result as what we are usually taught in Stats 101. We need here informative priors and sensitivity and specificity, and we need to obtain them in a way that is that reflects that we don't know these values as constants, but with some uncertainty. In what I will share with you, all parameters were given vague priors, except for sensitivity and specificity, such that our commonly expected frequentist result is here only affected by sensitivity and specificity and nothing else. So going back to the IARC monograph and their table with their best guesses, this is our group's approach to eliciting priors from it, not just taking constants or summarizing these values as constants for bias analysis, but saying that we want to have a beta prior here, which is a conjugate of binomial. Why is this important? It's a convenient statistical distribution to work with for those who are not familiar with, if we want to estimate proportions. If we start with that beta distribution as our prior belief, we are guaranteed to get a distribution of a proportion, which also has bounded between 0 and 1 as the result of our calculation, which is really nice. It will be a proper distribution. Now, beta distribution has two parameters, which intuitively means we only need 2 percentiles from experts to fix those two parameters. We basically said that the mode of beta distribution will be the average of best guesses. So we sort of said, okay, let's say that on average experts are right, individuals may vary, but on average, let's say they're wise enough to be average out to correct value. And we also took 2.5 percentile, so the lower bound, which is what we thought the experts meant, and averaged those out for each of the 4 misclassification parameters. And if we fix those 2 percentiles, those 2 proportions, let's say, we believe that mode is 0.95 and lower bound is somewhere 0.75, we can feed those 2 numbers into our function that, or unless we want to do this by hand, that will give us alpha and beta shape parameters of beta distribution. And then we'll have a nice shape that describes what our belief in this case is about distribution of sensitivity and specificity between cases and non-cases. And this is what this looks like. So we went to this procedure, and what you see in front of you are the illustrations of the shapes of prior distributions for cases and controls. cases are in red, and controls are in blue. So here on the left-hand side, we have a plot for sensitivity, and it tells us that if we average beliefs of experts that IARC employed and express their beliefs as beta distributions, then sensitivity among cases is slightly better than sensitivity among controls. This is what our intuition told us as well. This is how it was in the breast cancer example as well. If we look at specificity, those distributions are a lot closer, but here controls are believed to be more specific in reporting their exposures than cases. So they lead to fewer false negatives. So this accords with our intuition, but is now captured by statistical functions that we can work with inside Bayesian machinery. So a little bit more about how Bayesian adjustment works. Let us recall that our data in this case is the number of cases and number of controls from a table way, way back. And we can observed counts of exposed cases and controls can be modeled as binomial distributions. So C's and A's are counts from our 2x2 table. These are observed counts that are related to a number of cases for which we can find these values of pi, pi naught, and pi 1 that fit. So these are estimated proportions. It's very simple in a sense that this is what we do all the time as analysis of these studies. So if we can estimate these pi 1 and pi naught, then we can calculate odds ratios from this. These are odds ratios from observed data. That is straightforward. We want to know true probabilities though instead, so we need to add something to it. So I've just described data as a Bayesian apparatus sees it, but we need to add something to it, which is our priors. And here we are helped by this realization that true exposure prevalences, these R values, R1 and R0 for controls and cases, respectively, are related by simple algebra to observed prevalences, pi's, as well as P and P values. And there's a typo here, there's a Q missing there, that relate observed sensitivity and specificity to true prevalence. I apologize. There's a little mistake here in notation. But the big picture here is that you can calculate true prevalences from observed prevalences and sensitivity and specificity if you know these values. And then the trick becomes is finding an algorithm that picks out from our distributions so-called good guesses of true exposure prevalences and as well as sensitivity and specificity. And that magic is all covered in textbooks on the matter. Here, Monte Carlo Markov chain with Gibbs sampler works. This is a textbook case from that was developed years ago where this all works out quite nicely. So if you look at Bayesian adjustment, it's summarized here. We get averages of true odds ratio at the top of this table with estimate averaging out to about 1.1, with a 95% of true values falling somewhere between 0.7 and 1.8. This is the main result from this table at the top, but as a bonus, we also get posterior distributions of sensitivity and specificity for cases and non-cases, as well as, of course, these true prevalences, which were used to calculate odds ratios. And these sensitivities and specificities are useful in our future work if we want to follow up this study with a new case control study that uses similar exposure assessment methodology. Again, this was accomplished through a dozen lines of R code following textbook applications without any computational issues. So we applied essentially a reliable statistical method to arrive at these estimates that integrates diversity of opinions of experts into producing bias-adjusted odds ratios. We also conducted prior sensitivity analysis when prompted by a reviewer of our article. the main result is at the bottom of this chart. This is what I showed you in a table a second ago. Above it, results 2 and 3 have exactly the same location or mode of sensitivity and specificities, but while allowing greater uncertainty around those values. So that's 2 and 3. Unsurprisingly, it has the same triangle in the middle, which is the median, and wider bars, which is 95% credible range as our main result. Then what we did, we said, well, what if expert 4 is correct? Expert 1 is correct, so that's case 4. What if expert 2 is correct, which is case 5? And what if expert 3 is correct, which is our result 5, 6, and 7. Sorry, I just messed that up a little bit. So number 4 basically says, what if we were more certain than IARC experts about sensitivity and specificity? So you get shrinking of the credible interval, essentially the same result. So cases 5, 6, and 7 takes each expert as their own right. It says all the other experts were wrong. What do we get from it? What we get from it is that some experts suggest on average excess risk, so that's excess per 6. Some reduced risk, based on analysis 7, and some is somewhere in between. So that'd be analysis with expert 5. And analysis 8 here is, remember I told you we needed only 2 percentiles to set beta distribution from across experts. We chose a lower bound. We could have chose upper bound. So this is essentially a mirror of the main result at the bottom of the table, but using 95th percentile, 97.5 percentile, sorry, as fixed as an upper bound in averaging expert opinions. So all of this, in my opinion, comes up to pretty much the same answer as I'll argue in a second, but basically indicating that our main conclusion is robust to how we treat expert inputs, provided we take proper accounting of uncertainty around calculations that we end up with. This is what I told you in word. So interpretation of this all is OR is greater, naive OR is greater than any other estimates here. IARC's simple adjustment only addressed point estimates, and it pulled it down from that result to about 1.1. Our Bayesian analysis pushed it down to also about 1.1, but with wider uncertainty interval than that of IARC, reflecting truer uncertainty in these calculations. And just there for you, there's a reminder for you of where cohorts lay in this continuum. So it is my contention to you that by adjusting for recall bias here, we basically we are resolving heterogeneity in evidence that exists between cohorts and case control studies, community-based case control studies in the question of ovarian cancer and talc use. And this is not the first time that it happens. It happened to my research group before, and I think other people who work in this realm will report that it is not uncommon for heterogeneity of evidence to be resolved through bias analysis, which should make it nicer for regulators to deal with. Limitations, we did not adjust for confounding here. It can be done, and IARC attempted to do it by, again, using a constant to adjust. This can be done better by accounting for uncertainty and confounding, and this is part of my ongoing research. How sure are we that the priors were elicited in the least biased ways? Well, we don't know that. The method for which IARC experts, under which IARC experts operate, is not disclosed to us, and we took them as fair priors for this problem. But there's a vast literature out there on how to correctly or how to robustly elicit prior beliefs, and epidemiologists would be wise to engage with that. There's a lot to learn there from other disciplines that have done this work. There was some heterogeneity between studies that were pooled, different exposure definitions, different effect estimates, and that in principle could be addressed through meta-analysis of individual studies, which each adjusted for exposure misclassification and then pooled. Again, this is the future of it. There's publication bias and invested degrees of freedom bias, which is always present in these calculations. It's all done by humans, so we need to be mindful of choices that are not available to us for quantitative adjustment. in both publication of the results as well as what is done with them. And that applies to our work as well. We need to be, anybody who criticizes this work should tread a fine line between analyzing whether our math is right versus whether some of the choices we made based on our a priori beliefs could have been better defended. And I think that would be a very important conversation to have. There's an interesting postscriptum to that after work was submitted and basically accepted for publication, pending some minor revisions. UK Health and Safety Executive also reached a conclusion that limitations of the bias due to biases in epidemiological literature here in this question of talcum and ovarian cancer as such that studies essentially not very supportive of the association. There's not a clear signal here that is ripe for regulation. That is how I read this January 2026 document. Well, what are the larger implications of all of this for the SIG and for those people who don't really care about talc and related issues? Well, I'm very curious to know whether IARC would have reached different conclusions if they used more theoretically justified method to deal with recall bias. We don't know that. Maybe it wouldn't have made any difference, but it would be good to use the best possible methods on the highest stage. It remains to be seen whether our result will make any difference. I think those discussions are ongoing. European Commission is the first one looking at it, as far as I know. It really is a wild west for bias analysis right now. It sort of came into, with IARC publishing their book, I think it's really finally entering mainstream. Should we be excited or scared? Some people are afraid of weaponization of bias analysis. These are important conversations to have, and our SIG is a very good forum for that, and so is HESI. But I also hope that those of you who came here, and I'm very gratified that almost 200 people attended here, at least you'll pair up and have this conversation with your colleagues, so we have at least hundreds of conversations going on how do we proceed in this wild west of bias analysis. Of course, I'm mostly interested what you think about it, and one of the ways in which we can make that happen is by encouraging you to submit your work on bias analysis to a special issue of journal in Journal Global Epidemiology. I happen to be editor-in-chief of it. David Miller kindly agreed to lead special issue on the bias analysis in particular. We opened for business as of March 1st, accepting publications for about a year. And I strongly encourage you to submit your work on this topic here. And I can guarantee you both critical and open-minded review of your work. Any of you who know the journal will appreciate that it strives to publish methodologically rigorous work, regardless of any perceived importance or implication of findings. If math is right, at least we cannot find a mistake in math, we'll publish it. And I would like to close with that, go to my other picture, which I think is more serene and interesting, and open the floor for questions. Thank you.
Great. Thank you. Thank you very much, Igor. A few questions have come in on that. I encourage folks to add more if you have. Now that just type in the Q&A box and they'll show up here. I will mention just quickly, there are several questions came in about the slides and availability. They will be made available, the slides both individually as PDFs, as well as the recording on both the HESI website and the ISE eSig website, the special interest group on QBA, probably certainly by next week on that. So I'll just say that to folks on that. In terms of questions, I'll kind of go through them. We have probably about 6 minutes or so I may jump around a little bit. Just one question is, I'll read it to you, Igor. Is it fair to say that epidemiological data gathered in an occupational setting, for example, NIOSH, is more likely to have higher sensitivity and specificity based on the rigor of the reporting and the questionnaires relative to the general population? So any thoughts on NIOSH type or industrial hygiene type measures?
No. We in occupational epidemiology have not, there's no evidence that we've done better than people in other realms. And it all needs to be studied empirically on a case-by-case basis. Literature reviews of this particular matter that go back to work of Kate Teske indicate a very diverse performance in occupational epidemiology. It's all context and method specific. So you cannot draw any comfort from it being government based on occupational.
Okay, thank you. Another question, and we may go a little bit over. There are not a whole bunch. There are 6 or 7 questions, and hopefully we might be able to, if it's okay with you, Igor, go over a little bit, maybe 5 minutes or so on that is my guess. Another question is, can you elaborate on how sensitivity and specificity were quantified in the SHIFT study? And maybe I'll expand that a little bit to myself, just asking in terms of ways if epidemiologists are interested in looking more at sensitivity and specificity, what kinds of things can they do on that?
So in shift work study, again, I was not involved in it.
Mhm.
I only helped a little bit with some calculations on it. My understanding is that they used employee records and compared them to recall. So they actually knew which shifts people worked in healthcare setting and
Mhm.
cross-tabulated that with what was reported in questionnaires.
Okay. And sometimes they use sub-studies or gold standards on that with a
You need to
section.
seek gold standard wherever you can. Even
Yep.
if it's imperfect, you can still do a lot with it.
Yep. Great. Okay. Another question, just when you mentioned vague priors, are those the same thing or similar to uninformative priors?
Yes, pretty much. I mean, there's a great debate among statisticians about prior invariance on different scales. But yeah, so here you basically you can for one of the things we assumed in our work that prevalence of exposure among controls was anywhere between 0 and 1. I mean, it's ridiculous, but it's because we know it's, but we try to be really safe and not introduce any bias on that front. And
Mhm.
prior and odds ratio was somewhere between like zero point 0.1 and 10, so basically ridiculously wide, so that data had complete control as to where to place it.
Okay. So, another question is, thanks for the talk and the thorough analysis of this topic. How strong was the assumption that cases were better at remembering talc use in your Bayesian analyses? I think it's certainly a possibility, but I think we really don't know without a validation study. They may just as well be over-reporting or misremembering.
Okay, so that's a great question. So if you remember my plot of distributions of sensitivity and specificity by case and control status, they overlap here. So we don't make a strong assumption of them being very different. And that is supported by, say, work in the shift work study. The difference was 5% on average, right, with wide distributions. So we don't make a very strong assumption here, unlike any analysis that is used as a constant, which does not allow for any overlap at all. It basically says, absolutely, yes, cases are worse. We didn't do that. We allowed them to switch places depending on the individual. Yes, it'd be wonderful to have validation studies, but modern statistics advanced to a point where we're allowed to use our subjective judgment in a rigorous manner. And that's where Bayesian, pure Bayesian analysis come in. There's not a fringe activity. It's a legitimate, respected approach to statistical analysis. So even while we seek validation data, we should remember that when we use these pure Bayesian priors, there are checks and balances in the data on what is allowed. So
Okay.
David and I were part of experience where we as experts made very silly assumptions about one misclassification parameter, and we were harshly corrected by the data. So these checks and balances exist inside that Bayesian machinery.
Yep. Okay. Let's see. Another question is, in your Bayesian formulation, are you assuming prior independence between sensitivity and specificity? Is there any thought about putting a prior on the correlation between the two?
There's a lot of thinking about it. It's a fantastic
Yeah.
question. In
Yep.
fact, in Tim Lush's approach and some of the approaches, I think Sander Greenland was an advocate of that. There is a correlation imposed on sensitivity and specificity, saying that if since by case status, right? So if you believe that sensitivity is 0.5 in cases, in controls, it tells you something about sensitivity in controls as well immediately, right?
Yep.
So that can be done. It's not a textbook interpretation, so we assumed independence. Part of the difficulty with that approach is that it's easy to you can do probabilistic bias analysis, various correlations. That's pretty easy. Tim Lash has software that does that. My difficulty with that is that we know very little about what those correlations are.
Mhm.
So from Bayesian perspective, I would want to put a vague correlation prior in that correlation and see where the chips may fall. It's a
Mhm.
very good direction for us to go into. And it would be really fantastic if some of the validation studies that we do have could be informative about that.
Mhm. Yep. Okay. Thank
I
you.
think there might be.
Yep. Great. Okay. And again, I'll just say QBA webinar series, a survey. Please take a picture of that and tell us kind of what you're thinking on that. Another question is, and where does your cohort pooled estimate come from? That's not from the pooled paper and doesn't include more recent publications.
It came to us from publications available at a time. I know the sister's study has a different estimate, and
Okay.
that's not included in the latest ones.
Okay.
That study is an outlier, and exactly what it means remains to be determined.
Okay. And I guess one of the things to point out though is that it's all clear in terms of what you used and people can object to it or not or agree with it or not on that. So
Absolutely. All the code is out there. You can repeat your calculations very easily.
yep, yep. Okay. Another question. Many case control studies show associations between glyphosate and non-Hodgkin's lymphoma, but not cohort studies. Has anyone applied these methods to this discrepancy in findings?
As far as I know, nobody has applied those methods to those studies, but there could be a paper that I'm not aware of.
Yep. Okay. You mentioned that IARC didn't share their method, but can you share some methods to elicit priors, sensitivity, and specificity, which have been accepted by the scientific community, papers or reports or others on that?
Yes, I can share methods that are used to elicit probabilities. There's a whole R macro and there's extensive documentation from Sheffield Shelf that does that. I mean, there are textbooks,
Mhm.
chapter in Moya's textbook in elementary, by statistical analysis on how to do it. It's an active area of research. Uh,
Mhm.
and the key point here is that you need a methodology which documents both the questions that were asked and materials that were provided to the experts. That's elementary. And beyond that, there are many methods out there. And perhaps we can make them available through SIG, but this is literally like a package with documentation how to instruct experts to elicit probabilities of all sorts. There's no gold standard, but it's an active area of research.
Mhm. Okay.
So
Okay.
you could do better these days if you were motivated.
Okay, and maybe that's something we can kind of have you kind of produce a list of the references, and we can send it out to the members on that. Just two more questions, it looks like. So we should, great talk. How might this work generalized to discrete exposures with multiple levels or to scenarios with continuous outcomes?
It can definitely work with discrete variables. I mean, there are papers and statistics written on that. We didn't tackle that, but there's literature on it. With continuous outcomes, um, if outcome is not binary, it can work, obviously. There's no fundamental issue with math if you replace linear regression with logistic regression. Things are
Mhm.
simpler with linear regression, in fact. So that can be all worked out. Yeah.
Okay, okay. And which is obviously quite useful because the continuous are better measures than dichotomizing or so.
Yeah,
And
absolutely.
then the last question so far basically is have you tried QBA on other data other than recall and actually on continuous variables? So other
Well,
data.
I published on recall bias before
Mhm,
in another setting. I've done numerous adjustments for binary misclassification in case control studies. Um, so that is all out there in the literature. Continuous variables have done some work on measurement errors and biosensitivity analysis in cumulative exposure.
mhm,
If people are interested, there's work on Parkinson's disease and solvent exposure in Finland. Uh, Salman is the first author. It came out a couple of years ago. That's an example of quantitative bias analysis, which is applicable in a setting where statistical theory doesn't really exist for Bayesian adjustments.
Mhm.
But we were able to do quantitative bias analysis to run some simulations. So all of this exists, and
Okay.
I've done it, and others have done it. Like the whole
Okay.
regression calibration approach in nutritional epidemiology is based on alignment of continuous measures. So there's a
Yep.
ton out there. So if you have a particular problem that keeps you up at night or motivates you professionally, bring it to the SIG, and we'll kind of, if we don't know what the answer is, we might find somebody who does. All
Yep.
advertises through the SIG and connect you.
Yep, great on that. And I believe the spring speaker, the spring 2026 speaker will be talking a little bit about continuous variables as well in their topic on that. And I think that's all the questions now, and it's 12:05, so kept pretty close to time. Want to thank you, Igor. I'll turn it over to see if Sandrine has anything to say. I'll certainly encourage folks to try the webinar series. We will be sending. I'll ask you about sending out the links, basically, for example, Sandrine. But thank you very much, Igor. It was a wonderfully informative talk, and hopefully, folks will kind of learn from it, and we'll learn together as we continue to kind of expand the field in QBA and make it more widely used. So I'll turn it to Sandrine to close.
Yeah, thank you, David. Well, nothing to add, but yeah, reach out to David or to me if you have any questions about the SIG or about HESI, about what we do with the Environmental Epidemiology Committee at HESI, or questions about QBA. And yeah, like Igor said, we can maybe connect you with people who have answers for you. And yeah, thank you so much, Igor, for this great talk, very clear, and thank everyone for joining today.
Right. Okay. Thank you.
Thank
Thanks,
you.
everyone.
Bye bye.
Bye-bye.
Bye.